Okay, sorry about that. My computer wasn't working so well. But what I was trying to get at here was here's the answer key for worksheet 3, and my question is that we talk about the voltage drops, and across the battery they say it's positive, across the resistance negative. Not sure why it's negative, but I guess the sum has to equal 0. So anyway, I just don't remember that on our previous worksheets we did it that way where the resistor voltage drop was negative. Another thing I wanted to bring up here in the screencast was that the lab went well, the required lab, which was the series and parallel circuits, and I did get some of the resistors in advance of the class, and that was great. And it was kind of interesting because I left the batteries plugged in across the 10 ohm resistor, and that was a problem because there was quite a bit of current, lower resistance, and so that heated up quite a bit. And I guess one question I had was heating up or even lighting up. I guess lighting up if it's a incandescent filament like the long and round light bulbs. That's due to lighting up is due to heating up, and so the heating up that's due to I guess greater current, you could say, but then also, I guess it comes down to the power that's just the energy dissipated over time. But I guess it's common for me to say, oh, the current's greater, so the bulb's going to be brighter. But I think we have to be careful of doing that because you can also increase the resistance of something, and that makes a resistor hotter. And so, for example, if you have two equivalent currents going through two different resistors, the resistor that has a larger resistance is going to become hotter. And so I guess the heat or the brightness depends not only on the current, but also the resistance. And I guess at the same time, it would depend on the voltage drop. So I guess all three of those things, current, voltage drop, and resistance, determines power, and thus that determines the brightness or the hotness of your resistor. And so for this lab here, the Ohm's Law lab, this one I'll come back to here in a minute. But the one question I did have was the bottom of page 10. Yeah, here, this was a very interesting sort of derivation, looking at the area under the curve for, I guess, an Ohm's Law curve. And so that depends whether or not it's an ohmic device or a non-ohmic device. And so with a light bulb, it seems like the linearized graph of velocity versus current squared will give you a slope that represents the resistance. But that, since the resistance changes for a bulb that's getting warmer due to thermal effects, then you will have a non-ohmic device. And that will result in a power that's a little bit different, which is the area under the curve. So I also wanted to just kind of talk about the lab a little bit. This lab, I want to do this lab. I guess we didn't have this lab assigned to us this week. I just didn't have time to finish it. I read it, but I just didn't have time to do it. I do have the materials, and I'd love to do it because I think this would give me a better understanding of resistivity. And my week 9 webcast was a little bit on resistivity. And so this would really, I think, kind of sink in a little better. I guess with the students, I'm wondering which labs if I had limited time, which labs to do and which labs not to do. So some of these optional labs, I guess I would have to forego. But this lab here, which was one of a lab that's not optional, a series and parallel arrangement, this does seem pretty critical to do with the students. And so I guess what I'd like to, I'm not sure if you're seeing this screen, but anyway, so the series and parallel arrangements lab, straightforward. Everything seemed decent. Don't have any questions. Now it's really starting to work better for me. It was interesting to think about the use of the ammeter, and it wasn't that clear how to hook that up, but the ammeter needs to be put in series. It seems because it has a smaller resistance, so it doesn't hinder the current. Whereas the voltmeter needs to be put in parallel because it does have a high resistance. And so if you put it in parallel, then the voltage drop across the branches, the voltmeter branch, and then the branch of the original circuit would be the same. So it does read, give you a true reading of the volts. But then the current would be split if you put the ammeter in parallel. And so that would not give you a true reading of the current in the original circuit. Let's see. And so the readings came out to be fairly decent. I thought it was very interesting, the idea of how the voltage drop across the resistors for the parallel circuit and even the series circuit, the sum of the voltage through the resistors did not equal the voltage drop across the battery terminals. And so that suggests that there is some voltage drop through the wires, albeit small. I thought that was an interesting point. And I also thought it was an interesting way to derive the idea that the equivalent resistance for resistors in parallel is 1 over total resistance equals 1 over the resistance through resistor 1 plus resistor 2 plus 1 over the resistance through resistor 2 and so on. You can divide out the voltages in your equation of I equals V over R. And since the voltages are constant, voltage drop is constant for a parallel circuit across any of the branches, then those can be dropped out, that term. And so then you do get the equivalent resistance equation. That is somewhat, confusing, but it seems like this is an interesting way to derive it mathematically. That seems to make sense. And so I think I'll stop there and wait for class.